Hey, Alex from GMAT Ninja here. Welcome to the second video in our geometry series. This is GRE Geometry Part 2. So the goal of this video is to cover a lot of the content that we discussed in GRE Geometry Part 1, but apply it to more complex, more involved questions. So we'll hit some new content along the way, polygons, sectors of circles, but again the focus is going to be taking things we already know, formulas and knowledge we've already accumulated in Part 1, and apply them as the questions start to get more complex. So some themes we'll run into as we do that. Algebra is often your friend, so translating the statements you've been given into algebraic expressions, thinking about what algebra tools do I have that can be useful here, is often a useful path. Sometimes these questions look like geometry at first glance, and it's fair to say that they are, but when you peel back the layers, you find, well, the challenge here is really working your way through the algebra. So you could say this is kind of like an algebra question, but disguised as geometry. Another big theme, stay flexible. The first solution path that occurs to you might be the most efficient, but in a lot of cases it may not be. So the goal that we hit again and again with these questions is, can we look at this question from different angles? What are different approaches we might take to work our way towards the answer, and which one is going to serve us the best on a test? So there's going to be 8 questions total. They're going to get more challenging as they go. Now, all of these questions will be more challenging than the ones that we had in Part 1, and particularly towards the end, even if you're looking for an elite score, 165, 165 plus, you should find some challenges. On the other hand, if this video is moving a bit too fast or referring to formulas you're not sure about, feel free to check out GRE Geometry Part 1. So we'll give you a minute 45 seconds for each question. Feel free to pause the video if you need more time. On the other hand, even if you work your way to the right answer, you may still want to check out the explanation, see if you can get any pointers for how to maximize and optimize your efficiency on these questions. All right, great. Let's take a look at the first question. All right. In triangle ABC, the measure of angle A is 92 degrees. Which is bigger, quantity A, the length of side AB, or quantity B, the length of side BC? Okay, well, let's get a sketch of this triangle and see if can I figure out anything based on an idea of what this is going to look like. Okay, they don't give me a sketch, so it seems like a good place to start. So what is it going to look like to have a triangle with an angle of 92 degrees? Okay, so I don't need to obsess over being super precise. How can I draw exactly 92 degrees? I'm not sure. But let's try to get a good approximation. So let's think about a 90-degree angle. Okay, a triangle with a 90-degree angle looks something like this. So if it's a 92-degree angle, it'll be a little bit more than a right angle. So let's say something like that. Angle A is a little more than 90 degrees. Okay, now what about sides B and C? Well, they don't tell me which of those two, so I'll just assign those. Okay, angle A is 92 degrees. Okay, so based on my drawing, it would look like the length of side BC is longer than any of the two other sides. Okay, but can I trust that? Is that just, the way I drew this, it happens to be the case, but, not always going to be true? So let's see if we can confirm that side BC has to be the longest side. Okay, and let's look at a familiar triangle, again, a familiar right triangle, a 30, 60, 90. See what that tells us about the relationship between sides and angles. So notice if we assign that familiar formula x to x root 3 to 2x, well, notice the smallest side is opposite the smallest angle, right? X is opposite 30 degrees. Okay, the longest side, 2x, is opposite the largest angle, 90 degrees. And the middle angle, 60 degrees, is opposite the middle side. Okay, so that sort of confirms for me what I was already suspecting by looking at my drawing here. Yes, this is a rule about triangles, shows up a lot on the GRE. The longest side is opposite the largest angle of any triangle. The smallest side is opposite the smallest angle, and the side of medium length is opposite the medium angle. Okay, so can I confirm that 92 degrees is the largest angle? Well, what do I know about angles B and C? Okay, well, I don't know their actual measures. But if you think about what does their sum have to be, well, the sum of all the angles in a triangle is 180 degrees. So B plus C has to be equal to 88 if they're going to add up to 180. Okay, so if B and C together are 88, well, each of them separately has to be less than 92. Okay, so that confirms, yes, BC has to be the longest side because it's the side opposite the largest angle, so the answer to this one is B. Okay, so any take-homes for this question? Well, if they don't give you a drawing, not a bad idea to give yourself a sketch so you can kind of visually understand what's going on. And while you don't want to obsess and you can't be completely precise, it's nice to reflect what you can from the information in your drawing. Okay, in this case, 92 degrees, I know it's going to be a little more than 90 degrees, a little bigger than a right angle. Now, it's also nice to know that law about triangles, right? The longest side opposite the longest angle, smallest side opposite the smallest angle, true for any triangle you're going to encounter. All right, great. Let's take a look at the next question. Okay, rectangle ABCD has an area of 20 square inches, and the length of AC is 9 inches. What is the perimeter of ABCD in inches? Okay, so sometimes on the GRE, when you encounter a geometry problem, it's actually kind of an algebra question disguised as geometry. So if we consider that case, that would suggest, let's see if we can get algebraic expressions for this information we're given in the question. Okay, so a good place to start with that mindset would be, I'll define x and y on this diagram. I'll say AD is x, CD is y. Okay, because it's a rectangle, opposite sides are the same, so I can also say BC is x and AB is y. I also know that in rectangles, all the angles are 90 degrees. So I'll mark that on my diagram too, and I'm told AC is 9 inches. Okay, So let's start translating this information into algebra if we can. So if the area is 20 square inches, well, length times width gives me the area of a rectangle, so I can say xy equals 20. What about the fact that AC is 9 inches? Well, notice when you draw the diagonal of a rectangle, you create a right triangle. And you can use the Pythagorean theorem to relate the sides of a right triangle, so that will help me write an equation for that other piece of information. I can say x squared plus y squared is equal to 9 squared. So 9 squared, 81. Okay, so I've successfully translated these numbers into algebraic expressions, but let's keep going. Let's come up with an expression for what we're solving for. Right, they're asking for the perimeter, so what would that be in terms of x and y? Okay, well, if you add up all the sides, that's going to give you the perimeter, so I could say x plus y plus y, otherwise known as 2x plus 2y. Or I could simplify that as 2 times x plus y. Okay, so essentially that's what I'm trying to solve for. That's the perimeter. Okay, so now notice I have a specific goal in mind, right? I could have, at this point, just started simplifying things, but then I wouldn't have had a specific idea of where I'm headed. Okay, I know this is exactly what I want to try to find out. Okay, so one thing that occurs to me is, well, I could just try to solve for x. If I know x, then I could obviously plug it into one of these equations, get y, and then I'd find the perimeter. Okay, I also notice I have these two variables, x and y, and I've got two equations. So substitution jumps out as a possibility. I could solve for x with this equation and then plug it into this one. Okay, but if I think down that path a little further, well, x is 20 over y, and then I'd have to square 20 over y for x, and then I'd have all these big numbers. 20 squared is 400, and I've got to deal with 81. It's starting to feel kind of ugly. So I don't love that path. So before I dive into that, let's consider if there's any alternate way to get to a solution. Okay, now notice I was kind of assuming that a good place to start would be to solve for x, but notice I want x plus y. So maybe there's a way to work my way towards that more directly. Okay, so do I see any relationship between this information, this expression here with x plus y? Well, I notice I have x squared plus y squared. That's kind of like x plus y. Okay, so maybe I'll do some algebraic manipulations on this to see if I can make it look anything more like the information up here. Okay, so instead of, again, my thought process here is, instead of jumping into some algebraic process that's going to get really messy, let's experiment with this algebra a little bit and see if there's a simpler path. Okay, so could I make x plus y look anything more like this information up here? Yeah, let's square it out. So x plus y squared equals x squared plus 2xy plus y squared. Okay, so if I could find this, I guess I could just take the square root of it and it would give me x plus y, and then I'd be in good shape to find the perimeter. Okay, so if I could find this, I'm in good shape. Does this information help me figure this out? Looks pretty good, right? That x squared plus y squared I know is 81, 2xy, well, if xy is 20, 2xy is 40. Okay, so let's apply that knowledge. X squared plus y squared is 81, 2xy is 40. Okay, so x plus y squared is equal to 121. Take the square root of both sides. X plus y is 11. The perimeter is 2xy, so that tells me the perimeter is 2 times 11, or 22. Okay, so that tells us the correct answer to this one is C. Okay, so any take-homes from that question? Well, notice I got started by translating this information into algebra. It looks like a geometry question, but at the end of the day, it's all about working through the algebra. So I assigned x's and y's. I was careful to assign the information, including what I was looking for. Then I considered different paths, right? I didn't just jump into the first thing that occurred to me, solving for x, plugging in here. I thought the numbers might get really big and ugly. I'm not sure I want to deal with that. So then I started doing some creative algebra to see if, okay, well, is there a way I can work my way towards x plus y without solving specifically for x? Okay, now I squared it out. Did I know exactly what was going to happen? Not necessarily, but I had a feeling I could make that look kind of like the information I already have. And that's what, in fact, what happened. I get an expression that I can relate to this information. I plug in the numbers. I get x plus y is 11. Okay, important last step, I didn't jump, make a careless error, and pick A. Right? I always have that last step of, well, ultimately, what am I solving for? Oh, right, it's the perimeter. I had that expression written out. 2 times x plus y. And again, that leads me to the right answer of C for this question. Okay, great. Let's take a look at the next one. All right. So the rectangular solid ABCDEFGH has a line connecting point C and point E. If the length of edge AB is 10 inches, the length of BC is 2 inches, and the length of AE is 11 inches, what is the length of line CE in inches? Okay, so I notice this line that I'm given here is what I call the longest diagonal of a rectangular solid. Okay, so why am I saying it's the longest diagonal? Well, notice I could draw other diagonals in this shape. If I think about rectangle ABCD, I could draw a line from A to C. That would be a diagonal. If I think about this rectangle here, BFGC, I could draw from B to G or from C to F. Okay, but the very longest diagonal would be if I start the back left corner and I come to the front right corner. And notice I could draw another one of those if I started the back right corner and came to the front left corner, or even more, right? If I started at the top left corner A and went down to G. Any one of those where I'm crossing the whole figure, I'll call those the longest diagonal. Okay, so it turns out there's a formula for that, which is really handy for these types of questions. So to describe that formula, let's first think about how do you find the diagonal for a rectangle, and we'll see if we can extend that logic for a rectangular solid. Okay, so I'll think about a rectangle. It has all 90-degree angles. I've got a length and a width. Okay, now how do I find the diagonal of a rectangle? Well, let's say here's D, the diagonal. Now notice the diagonal of a rectangle forms a right triangle, so I can use the Pythagorean theorem. L squared plus W squared equals a diagonal squared. Okay, so in a rectangular solid, you could talk about a length and a width for sure. I'll say that this side here, DC, is a length, and let's say CG is the width. Okay, if DC is a length, then you notice AB would also be a length, right? Opposite sides of rectangles always have the same length. So here's an L, here's an L. If I look EF, that's also got to be an L, etc. But in any case, I can talk about how a rectangular solid has a length and a width. But notice they also have a height. Okay, so I could call FG the height, or again, BC would be a height. But whereas a 2D, whereas a rectangle, a 2D shape, has only a length and a width, rectangular solid has a length, a width, and a height. So it turns out to find the longest diagonal, I'll just call that capital D, of a rectangular solid, you want to do not just the length plus the width squared, you also want to include the height. Okay, so this is the general formula. It's useful for any rectangular solid, and it relates the length, the width, and the height to that longest diagonal. We'll call that capital D. Okay, so let's see if I'm given enough information to make use of this formula. So I'm told that the length of AB is 10 inches. Okay, so the length is 10, that's 10, that's 10, etc. The length of BC is 2. Okay, so BC is right here, so that's my height. So that's 2. FG also 2. Okay, so maybe I'll start writing these down. Length is 10, height is 2. I'm also told that AE is 11 inches. Okay, so AE over here is 11. That means this is 11. That means what I call the width is 11. Okay, so I'm given all three of those quantities. I can plug those in, solve for capital D, the longest diagonal. So L squared is 100, W squared, 11 squared is 121, height squared is 2 squared, 4. Okay, add all those up, that gives me D squared, so 225 is equal to capital D squared. Square root of that, I get 15. All right, so that leads me to the correct answer here of C. Okay, so any take-homes for this question? Well, bottom line, this formula can be very helpful when you're dealing with rectangular shapes, rectangular solids in particular. Okay, and what you do is you relate the length, width, and height to one of those longest diagonals. The longest diagonal in this case was EC, but notice you can draw more than one. I could also say FD, that would be a longest diagonal. AG, that would also be a longest diagonal. Okay, but no matter where it's drawn, this formula is often very helpful for these. Okay, great. Let's take a look at the next question. Okay, in the diagram, a regular hexagon is inscribed inside a circle. If the circumference of the circle is 16 pi, what is the area of the hexagon? Okay, well, maybe I'll start with the information I'm given. Circumference of this circle is 16 pi, and see what else I can figure out. Well, circumference is 2 pi r. So if 2 pi r is equal to 16 pi, that tells me r has to be equal to 8. Okay, so the radius of this circle has to be 8, so I'll draw a radius on there. That has to be 8. Okay, I'm trying to find the area of the hexagon though. So what do I know about this hexagon? Well, it's a regular hexagon. Okay, so that means all the sides are the same, all the angles are the same. If you remember from Geometry Video 1, there's some formulas you can use to find the internal angles of a hexagon, so that's certainly one route I could go down. But how am I going to get the area of that thing? So one way to approach complicated figures is to break them up into simpler ones. If you can find the area of the simpler shapes, then you can get the area of the larger, more complicated one. Okay, so this center of the circle here, notice because it's a regular hexagon inscribed in there, totally symmetrical shape, that's also the center of the hexagon. Okay, so maybe I'll draw some more radii. See if I can break this thing up into simpler shapes. Okay, so notice if I draw a radius for each of those vertices of the hexagon, right, I hit each of those corners, what I did was I broke up this hexagon into triangles. Okay, so if I could find the area of a triangle, that could be helpful. Maybe that'll work me towards the area of the hexagon as a whole. Okay, well, let's fill in for more. Is there any more information I can fill in at this point, based on what I know? So, well, all radii have the same length, so each of these radii is 8. Okay. So that tells me, maybe I'll just look at this triangle right here. Well, it's a isosceles triangle, right? Both those sides are the same, so both of these angles have to be the same. I'll call both of those x. Okay, anything else I know about this triangle? Right, I'm trying to figure out all the information I possibly can so that hopefully that'll allow me to calculate the area somehow, right? And I don't see a direct path at this point. I'm still in that phase of, can I just fill in all the information I possibly can? Does that give me a better idea of what's going on? Okay, well, remember we said this is a regular hexagon, so it's totally symmetrical, right? All the sides are the same, all the angles are the same. So that kind of tells me, all right, well then, all these triangles have to be the same too, right? It's only logical if I have a symmetrical shape and I divide it up in that manner, I'm going to be creating the same triangle again and again. So I'll just say this angle right here has to be the same for all the triangles, right? I'll just maybe call that y. So each of these triangles has angle y. Okay, so does that help me figure out maybe a value for y? Well, notice if you go all the way around a circle, that's 360 degrees. So if I add up all those y's, in other words, 6y, that has to be 360. So y has to be 60 degrees. Okay, great. So piece by piece, we're getting more information about this triangle. That angle is 60 degrees. Okay, can I figure out x now, these missing angles here, x and x? Well, notice the sum of all the angles has to be 180. So 60 plus 2x equals 180. If I solve that, I get x is 60. Okay, so not only is this an isosceles triangle with two sides the same, it's an equilateral triangle, right? All the angles are 60 degrees. If all the angles are the same, all the sides have to be same. So this is not just 8 by 8, but this missing side here is also 8, right? Equilateral triangle. Okay, and then again we said all these triangles are the same. So what do I have here? I've got 6 equilateral triangles, all with a side length of 8. So if I can find the area of an equilateral triangle with a side length of 8, that'd be great. I could multiply that by 6. That'll give me the area of the hexagon. Okay, so how do we do that? Let's think through an equilateral triangle and how to find its area. Well, I know that the area of a triangle is 1/2 base times height. Okay, so let's say that this is the base here. The base is 8. So then the height would be here. All right, I'll make a 90-degree angle with that side there. This is the height. Okay, so can I figure out the height? Right, if I could do that, I could get the area of this equilateral triangle. Well, remember all the sides, or rather all the angles are 60 degrees, so those are both 60. Okay, if this is a 90-degree angle, that remaining angle has to be 30. And that makes sense. When I drew the height, it makes sense that I would bisect that angle because this is a totally symmetrical triangle. Okay, great. So this height is one side of a 30, 60, 90 triangle. So maybe I'll draw that 30, 60, 90 right here. Okay, there's my right angle. This is 60. This is 30. I know the hypotenuse is 8. Okay, now if I go back to my ratios of the sides of a 30, 60, 90 triangle, remember the smallest side is x, the medium side is x root 3, and the largest side, the hypotenuse, is 2x. Okay, the hypotenuse here is 8, so in this triangle x equals 4. Okay, the height is the side opposite the 60, so that's x root 3, so that height is 4 root 3. Okay, great. So now I can plug that into 1/2 base times height, get the area of this equilateral triangle, and then I should be able to get the area of the hexagon. Okay, base is 8, height is 4 root 3, so 1/2 times 8 times 4 root 3. Okay, so 1/2 times 8 is 4. 4 times 4 root 3 is 16 root 3. How many of those do I have? I've got 6 of them going all the way around. So 16 times, 6 root 3, 16 root 3 times 6, that's what I wanted, gives me 96 root 3. Okay, and it turns out, there we are. So the correct answer for this one is C, 96 root 3. Okay, so any take-homes for this one? Well, notice the way I got started was to start writing down all the information I knew. And the more information I got, the closer I got to figuring out, okay, how can I get the area of this hexagon? Now, another useful thing was I've got a big shape here. I don't, off the top of my head know a formula for the area of a hexagon, right? It's probably going to be cumbersome to clutter my mind with all these formulas for different shapes, but if I can break it up into triangles, I'm in good shape. Okay, and then lastly, notice if you have the side of an equilateral triangle, you break it up into 30, 60, 90, you can work your way towards its area. Okay, now some people, they say, okay, well, if I know the side length is 8, then I can use my formula, which is s squared root 3 over 4. Okay, that gives you the area of an equilateral triangle. And sure, some people feel like it's useful to have that memorized. Personally, I don't like to clutter my mind with too many formulas. Not too much work for me to confirm that formula is right or just to derive it. Say, okay, if I have an equilateral triangle, break it up into a 30, 60, 90. That allows me to get the base and the height, and I'm in good shape. Okay, great. So after running through all that, again, that leads us to the correct answer of C for this one. All right, great. Let's take a look at the next question. All right. In the diagram above, a rectangular lawn is bordered by a path. The path has the same width all the way around the lawn. If the lawn is 8 meters long and 4 meters wide, and the area of the lawn and the path combined is 96 square meters, what is the width of the path in meters? Okay. So I'm asked for the width of the path. So I have this path going around a lawn. So let's start by defining a variable for that. Always a good place to start to know exactly what I'm solving for. So maybe I'll call that x. This width of the path right here is x. And they said it's the same width all the way around. So no matter where I go, that path has, let's just say, a width of x. That's what I'm trying to solve for. Okay, so let's see if I can translate any of these other numbers into algebraic expressions. Okay, looks like a geometry question, but at the end of the day, on the GRE, a lot of geometry ends up turning into algebra. Or another way to put that is, if you can successfully translate the geometry diagram into algebra, you're following a decent path, on a good path to reach the answer. Okay, so what else am I told? I've got some numbers, okay. If the lawn is 8 meters long, okay, let's get that on the diagram. There's 8, and it's 4 meters wide. Okay, I'll put the 4 right there. I guess I've got 4s and 8s going around like that. And the area of the lawn and path combined is 96 square meters. Okay, so I've got an area of 96. Is that this inner rectangle? No, remember that's the lawn. It's both of these things together. Okay, so can I get an expression that involves x and ties together, 8, 4, and 96? If so, I think I'm probably in pretty good shape. Okay, so, well, the area of this whole thing, if I knew the overall length and the overall width, right, including this path, and I multiplies those together, that would give me 96, the area of the lawn and the path combined. So what is this length? Well, part of it is 8, okay, but notice it also includes the width of the path, so I've got x, but notice I've got x twice, right? I've got x over here to extend to this side, and then I have an x again over here, right? Or I'll just draw it again right there. Okay, so that total length, not just 8 plus x, for some reason that tends to be a common mistake, but in this case we want 8 plus 2x. Okay, and I could follow the same logic to get this side of the overall rectangle, right? I mean, I'm calling that w here, but don't confuse that with the width of the path itself, right? But we're calling that x. But this line right here, this side of the larger rectangle, what is that equal to? 4, and then I've got 2 x's again, right? An x down there, an x up there. Okay, so 4 plus 2x, and all of that is equal to 96. Okay, so in theory, this looks like an equation with a single variable. Let's see if I can solve it. Okay, so I guess I'll FOIL that out. 8 times 4 is 32. 8 times 2x is 16x. 2x times 4 is 8x. Plus 4x squared equals 96. Okay, these aren't the most horrendous numbers I've ever seen, but I don't love them. So I'm going to be extra double careful with each step I do, as I am for any calculation, to make sure I don't make a careless error. I know it's going to be very easy to do, so I'm going to double check everything. Okay, so can I combine like terms here? Yes, 16x plus 8x is 24x. And then I've got 32 plus 24x plus 4x squared equals 96. Okay, so before I go any further, I would love to shrink these numbers if possible, right? I feel like at some point I'm maybe going to make a mistake. It's also just not fun to work with all these big numbers. So I'm going to see, okay, can I divide all of these numbers by some common factor? Is there some common factor of 32, 24, 4, and 96? Okay, so 4 jumps out, 24, 32. Yeah, I believe that also goes into 96. Okay, so let's divide this whole equation by 4. Everything here gets divided by 4. So 32 becomes 8, 24x becomes 6x, 4x squared becomes x squared, 96 divided by 4, let's see, that is, I believe that's 24, but I'm just going to confirm, do a little sanity check here. Okay, do my long division, and yeah, 24 times 4 is 96. Okay. Okay. Little sigh of relief. That's a lot better, right? Okay, but I'm going to keep up my philosophy of let's double check every step. Okay, so I'm going to subtract 24 from both sides. Okay, that will allow me to set this, to create basically a quadratic equation here equal to 0, and then that's something in theory I can solve. So subtract 24 from 8, I get negative 16. Okay, so that all turns into x squared plus 6x minus 16 equals 0. Okay, so how did I get here? Well, translate the algebra very carefully and crunch the numbers very carefully, but don't get carried away. Ask myself, is there anywhere I can simplify, make these numbers smaller, make things a lot easier? I end up with a pretty nice looking quadratic here. Okay, so what are factors of negative 16 that add up to 6? Well, I think 8 and negative 2 would do the job. Okay, so x has to be negative 8 or positive 2. Okay, well, a negative number doesn't make sense for a width of a path, so x has to be 2. Okay, now what was I solving for? What is the width of the path in meters? Okay, x is the width of the path. That's how I defined it. So the correct answer is A. The correct answer is 2 for this one. Okay, great. So any take-homes for this one? Well, geometry algebra disguises geometry, right? We ended up doing a whole lot of algebra here, even though at first blush it kind of looked like a geometry question. But once I get my translations down, translate the information I have into algebra, define my variables, and then if I'm successfully able to work through that algebra, I'm in good shape. Just double check what I'm solving for. Yes, in fact, I was solving for the width of the path, which is x. And again, that leads me to the correct answer of A. Okay, great. Let's take a look at the next question. All right, multiple choice question here. In the diagram above, O is the center of the circle, and A and B are points on the circumference. If the length of line AB is 6 centimeters, what is the area of the shaded part of the circle in square centimeters? Okay, so I want the area of this shaded region here. Now, this shape is not something I'm familiar with. I don't have a name for it. I don't have a formula to find that kind of area. So is there another angle I can look at this question from? In other words, can I piece together this shape, this shaded area, using familiar shapes that I actually do have formulas for? Well, I notice I've got a triangle, so that seems like a good start. 1/2 base times height would work for that. Now, what about this shape OAB? This, basically I could call that a slice of the pie. Well, that's the sector of a circle, and there actually is a formula for that. So let's talk through that to see what this formula tells us, why it makes sense, then we can apply it to this question. Okay, so let's say I have a circle with like a central angle of x right there and has a radius of r. So if I want to find the area of that sector right there, it's just x over 360 times pi r squared. And again, x is that angle in degrees. Okay, so why does that make sense? Well, notice x over 360 is giving me the fraction of the circle that sector is taking up. Right, the bigger x, the bigger the fraction, the smaller x, the smaller the fraction. So kind of makes sense to say that x over 360, the fraction of the circle that I'm dealing with, times the area of the whole circle gives me the area of just that sector. Okay, now, while we're on this subject, let's talk about arc length. It's not directly relevant to this question, but it's something that could come up. So what is the arc length of arc PQ right there? Okay, so in other words, you could talk about the circumference of a circle that's going all the way around, but what if I wanted to go just from P to Q? And it's actually a similar formula. I'll write it down here. X over 360, so that gives me the fraction of the circle that I'm dealing with, but instead of times the area of the whole circle, it's times the circumference of the circle. Okay, and then that's going to give me what's known as the arc length. This here, that gives me the area of the sector. Okay, so here's a formula that's relevant to this question. If I can get the area of that sector, seems like a good start. And then if I subtract from the area of that sector the area of this triangle, I should be left with that shaded region. Okay, so what do I need to find the area of a sector? Well, my formula is x over 360 times pi r squared. Well, I know that x is 120, so that's good, but I'm missing the radius. So that's the question, what is r equal to right here? Okay, so is there any information that I haven't used yet that I've been given? Well, AB is equal to 6 centimeters. Okay, so that's the base of this triangle. Now I'd like to know the height, so I'll draw in a height. And if I could figure out that height, I could get the area. Okay, well notice I have an isosceles triangle here. That's one thing to note, right? Two sides are the same. Those are both radii, so they have to have the same length. Now if I draw the height, notice because I have this symmetrical triangle, it's going to cut this opposite side in half, right? So AB, which is 6, is going to be cut into 2 segments, each with a length of 3. Also, this height, if I draw it straight down, it's going to make a 90-degree angle. You know, by definition, the height should be, perpendicular to the base. So, all right, great. So what can I figure out about this smaller triangle here? Well, 120 is cut in half, so this angle is going to be 60 degrees. Okay, I've got a 60, I've got a 90. Okay, so I've got a 30, 60, 90 triangle, right? Those angles all have to add up to 180, so it's got to be a 30, 60, 90. Now keep in mind, the ratio of the sides for 30, 60, 90, x to x root 3 to 2x. Okay, great. So I know that this segment right here, not all the way across from A to B, but I'll call it from, maybe A to Z, if Z is that point right there. So AZ is 3. So which of these does it correspond to? Well, it's opposite the 60-degree angle. So that means it's the medium length side. Okay, great. So by breaking apart this triangle, I'm working my way towards the side lengths, which could, in the end, get me the radius. Okay, so going back to our 30, 60, 90, we know the medium length side, which has root 3x as its length, in this case is equal to 3. Okay, so x is equal to 3 over root 3. All right, I've got a radical on the bottom, so let's simplify that. Multiply by root 3 over root 3. I get 3 root 3 over 3, which is equal to just root 3. Okay, great. Once you figure out x, you're in good shape. You can figure out all the other sides. This side we already know is 3. Okay, the hypotenuse, 2 root 3. Okay, now the hypotenuse in my triangle, that's the radius. Okay, so I know that r, I'll get that over here, r is equal to the hypotenuse, or in other words, 2 root 3. All right, so by breaking apart this triangle, I was able to find the radius of the circle. Now I can plug that into my segment formula, my sector formula. Then I can subtract the area of that triangle, and I should be in good shape. Okay, so let's get the area of the sector. So that's equal to x over 360, so 120 over 360, so that gives me 1/3, times pi r squared. Okay, so times pi times 2 root 3 squared. Okay, 2 root 3 squared. Well, let's see. 2 squared is 4. Root 3 squared is 3. So 4 times 3 is 12. So 12 pi times 1/3. And that's equal to 4 pi. Okay, so I found the area of the sector. That's a good start. Now I want to find the area of the triangle. Well, triangle AOB has a base AB of 6. So I want 1/2 base times height. The base is 6. Okay, what's the height? Well, notice that's the side of this 30, 60, 90 that's opposite the 30. In other words, it's the shortest side of the 30, 60, 90. It's this one here. Okay, I solved for x. I found that it was root 3. So the height is root 3. All right, great. So 1/2 times 6 times root 3. The area of that triangle is 3 root 3. Okay, so now I'm ready to put it all together. The area of the sector is 4 pi. I'm going to subtract the area of triangle AOB, which is 3 root 3. I'm left with the shaded region. Okay, so 4 pi minus 3 root 3, that's as simple as I can get, and there's my answer. So the answer to this question is D. Okay, so any take-homes for this one? Well, notice to get started, if you have an odd shape, this shaded region here, it's not a familiar shape, it's not something that I have a particular formula for. What do? Try to work your way towards it by finding the familiar shapes, right? In this case, the familiar shape was a triangle that turned out to be basically two 30, 60, 90 triangles, and the sector AOB. So I've got a formula for the area of the sectors. I can break down this triangle into 30, 60, 90s, use my formula for the area of a triangle, put that all together, careful with my arithmetic, and then again, that leads us to the correct answer of D. Okay, great. Let's take a look at the next question. All right, let's check this one out. In the diagram, the square PQRS is placed inside the square ABCD. If the difference between their areas is 144 and the sum of their perimeters is 72, what is the difference between their perimeters? Okay, so I'm asked for the difference between their perimeters, and I'm given a bunch of information. Let's start by translating this stuff. If I can translate these words into algebra, get some equations up there, that could be a path forward. So I'll start with that first statement, if the difference between their areas is 144. Okay, so can I get an expression that translates to that statement there? Well, okay, these are both squares, so I guess I could call the side length of the bigger square x, then all these sides would be x. The smaller square, they've got different side lengths, so I'll give a different variable, I'll call those y. Okay, so the difference between their areas is 144. That means if I subtract, the smaller area from the bigger area, it should be equal to 144. Okay, so let's do that. The area of the bigger square would be x squared. The area of the smaller square, well, it has side lengths of y, so it should be y squared. And the difference between their areas is 144. Okay, let's just keep going, see where that leads us. The sum of their perimeters is 72. Okay, perimeter of the larger square, it has side lengths of x, so the perimeter of the whole thing, 4x. Same thing for the smaller square, 4y. Okay, the sum of their perimeters is 72, okay. The question is, what's the difference between their perimeters? Okay, well, I've got an expression for their perimeters. The difference, I'll just write that up here, 4x minus 4y. That's what I'm looking for. Okay. So one thought would be, Well, if I could solve for x and y, then I could get what they want. Can I solve for x and y? Well, I have two equations, two variables, so I guess I could mess around with those a bit. Maybe substitute solve for y, plug it in here. Okay, so I'll note that, but set it aside for the moment, because I want to look at this from every angle before I decide on which path I want to follow. I'm always asking myself, what's the most efficient path? Have I found it yet? Well, this seems like a lot of algebra, so I'll put it on the back burner for a sec. Any other way I can work my way to this besides solving for x and y separately? Well, could I get x minus y directly, right? Could I somehow solve for 4x minus 4y in a more direct manner without getting x and y on their own? Okay, so that's a question, and I notice that I have 4x plus 4y, so it somehow seems related. Now, I also can't help but notice this is the difference of two squares. Okay, so all those algebra rules, we're in geometry land, but in a way, this question is just an algebra question disguised as geometry. So keep in mind, your whole toolkit, even if it's a geometry question, maybe that algebra stuff will come in common. So just to review those, a squared minus b squared, a squared minus 2ab plus b squared, a squared plus 2ab plus b squared. Okay, so these are all common quadratics that it's nice to know how do you factor these, or if you see them in the factored form, how do you go back to this? Okay, so maybe to write these out, I'll go to the left. A squared minus b squared, remember that's a plus b, a minus b. Okay, that's directly relevant to this question. These two, I don't see them popping up in this question, but other good ones to be aware of. This is a minus b squared. This is a plus b squared. So whenever these patterns show up, I want them to kind of jump off the page, and I'll start thinking about, can I use this, the fact that I can factor these to my advantage? So let's see if that's the case here. Can I use x squared minus y squared to my advantage? Well, that would be factored into x plus y, x minus y. That's equal to 144. Okay, now all of a sudden, I'm noticing some connections here, right? This has x plus y in the formula. I know what 4x plus 4y is. This also has x minus y in the formula. I want to know 4x minus 4y. Okay, let's keep going with this idea of simplifying things. Okay, I could factor out a 4 here, or even better, maybe I'll divide both sides by 4. Okay, that would give me x plus y on this side. 72 divided by 4 is 18. Okay, I'm looking for 4x minus 4y, but could I simplify that to make my life easier somehow? Well, if I factor out the 4, notice if I find xy, I can find 4x minus 4y. So really, I could simplify my goal as, can I solve for x minus y? Okay, well here's x minus y. If I knew x plus y, I could get it, right? And that's what we found over here. Essentially, if we know the sum of the perimeters is 72, we can simplify that to say x plus y is 18. Okay, so let's proceed with what we figured out. X plus y is equal to 18 times x minus y equals 144. Okay, so 144 divided by 18, so that would be 8, right? 18 times 8 gives me 60 plus, 80 plus 64, that's 144. Okay, great. So x minus y is 8. Now, keep in mind, I don't want to jump the gun at that point and just pick the answer choice 8. In fact, that is an option that they offer me. But I'm trying to solve for the difference between their perimeters. Remember, it's 4x minus 4y, not x minus y. Okay, I'll plug that in here. That's equal to 8. So my final answer is 32. Okay, so any take-homes for that question? Well, the first thought, this is algebra disguised as geometry. And if I can successfully translate what I'm given into equations, that's a great start. Now, another thought, think about your path. A first thought might be, I want to solve for x and y separately. And while that is a path to solution, it's not the most efficient in this case. So you want to look at it from different angles, maybe play around with the algebra a little bit. If you notice familiar patterns, in this case difference of squares, see if you can take advantage of that somehow. Play around with the algebra, see if something falls out. In this case, I don't think I saw a path all the way to the solution when I factored this. I was just kind of experimenting to see what would happen. But as I did that, all of a sudden these connections jump out. I realize, aha, I can solve directly for x minus y. And then the last point would be, when you're really deep in this algebra, don't forget, before you pick your answer, remind yourself what exactly is the question asking for. It's great that I solved for x minus y, but what they wanted is 4 times that. Okay, if I do all that, leads me to the correct answer of C. Okay, great. Let's take a look at the next question. Okay, let's take a look at this one. 2 identical semicircles are inscribed within a circle and do not overlap. What fraction of the circle is shaded? Okay, so let's see if I can translate this statement here into some kind of expression so I have a clear idea of what I'm solving for. So the fraction that's shaded, so as a fraction, I guess on top would go the shaded area, and on the bottom would go the total area. So if I can somehow find what that ratio is, if I can find what that fraction is, that's what I'm looking for. Okay, now the shaded area, well, it's 2 identical semicircles. So if I put those together, I get one circle. So I could say really the shaded area is the area of the small circle. And then the total area, well, that's just this area of this big circle. Okay, so let's see, how would I solve for those? And notice they don't give me any numbers at all. So I'm not going to actually be able to solve for the area of the small circle on its own, or the area of the big circle on its own. Somehow I'm going to have to relate those 2 areas, see if I can find something that connects them, and that'll be my answer. Okay, so the area of the small circle, well, I guess I'll call the radius of the small circle little r, the radius of the big circle big R. Okay, so what I'm looking for is pi little r squared over pi big R squared. Okay, so the pi's cancel. So really what I'm trying to find is, little r squared over big R squared. So I suppose if I could find just plain old little r over big R, if I could get some value for that, I could square it, and that would give me the answer I'm looking for. Okay, so I'm trying to find the relation between the radius of the small circle, the radius of the big circle. So let's start drawing some radii and see if we can connect them up somehow. Maybe they're going to connect in some kind of shape, and I'll be able to figure out their ratio of little r to big R through that. Okay, so here's the big radius, here's a small radius. Okay, that doesn't seem to help too much. They're not overlapping in any way. It's hard for me to connect them. Okay, so let me draw another big radius. Okay, so now at least it's sort of hitting this smaller radius, but then the problem is, what's the length of that segment right there? right? If I could subtract that segment, then I could relate the smaller to the bigger, but I'm really unsure as to what that is. Okay, having drawn this, I'm tempted to draw this line too, but I don't see a heck of a lot I can do with that line. I mean, it does make a triangle. I suppose that's nice, but it's not a radius itself. Okay, so I feel like I'm barking up the wrong tree. Let's see if I can draw the big radius in yet a different place, right? This first place, pretty useless. This second place, tempting, but doesn't seem to be yielding much useful, any useful relations. Okay, let me do another one. So if I draw from the center to the corner of this semicircle, okay, now they're overlapping in an interesting way. So maybe I'll draw another one of those. Okay, now one thing I notice is I've made a right angle. Okay, so let's stop and consider how I know that's the case. Well, these two lines that I drew here, they're intersecting both corners of the semicircle. Okay, and whenever that happens, you know that you've made a right angle. So let me just emphasize that point. Okay, so here's the diameter of a circle. This right here is a diameter, right? Diameter of a semicircle. And if I draw two lines that hit the edges of that semicircle, no matter where I start, that's going to make a right angle. Okay, so I could do it on the bottom also. If I go like that, that makes a right angle. Okay, so that's a useful rule to know on the GRE. If I have a circle or a semicircle, and then I draw two lines to basically make a triangle, right, with the diameter being the hypotenuse, and these are the two legs, I know that that angle has to be 90 degrees. Okay, so let's label some of the sides here, see if we can start relating big R and little r. Well, that's big R right there. That's big R right there. These are both little r. Okay, now this is a right triangle, but notice it's also an isosceles right triangle. Two of those sides, those two legs, are the same. Okay, if I have an isosceles right triangle, I've got a 45, 45, 90. Okay, and the reason I'm saying that is, well, these two angles have to be the same. Because these two sides are the same, definition of isosceles triangle, all the angles have to add up to 180. So if this is 90, those need to be 45 and 45. Now, the great thing about a 45, 45, 90 triangle is the sides have this ratio x to x root 2. X root 2, longest side, that's the hypotenuse. These are both the legs. Okay, so in this 45, 45, 90, what is x equal to? X is equal to big R. So I'll move over here. The ratio is R to R root 2. Okay, so just to review what I said, if the legs are equal to x, the hypotenuse is x root 2. For my triangle, the legs are equal to big R. So the hypotenuse is equal to big R root 2. Okay, now notice that's successfully relating big R to little r, because I also know that the hypotenuse is the diameter of the small semicircle, or in other words, 2 times little r. Okay, so big R root 2 is equal to 2 times little r. Okay, so let me write that in a way that's kind of easier to manipulate. But I feel like I'm heading in the right direction, because remember, what we said was, if we can get the ratio of little r to big R, then we're in good shape. We can get r squared over r squared, little r squared over big R squared, and that's what we want. Okay, so big R times the square root of 2 equals 2 times little r. Okay, what's little r over big R? Okay, well, I've got little r on the top over here. Maybe I'll divide both sides by big R. Okay, that would cancel this out. Now I've got 2 times little r over big R. Well, let's get rid of that 2 on the right, move it over to the left. Okay, that's going to give me, let's see what that gives me. Root 2 over 2 equals little r over big R. Okay, great. So I fought my way to this ratio that I want. What do I get if I square that, right? Because little r squared over big R squared would give me the ratio of their areas. So little r squared would be 2. Big R squared would be 4. So 2 over 4 or 1 over 2. So D is the correct answer for this one. Okay, so that's one path to the solution. Maybe I'll go through another. If that made sense, great. I think there's another angle to look at this that may be slightly more efficient. Okay, so keep in mind we're looking for, again, little r squared over big R squared. And if we get little r over big R, then we can work our way towards that. Okay, so if I draw big R like this, okay, great. That was useful in this other solution path we had. But let's see if there's another way we can do it. Well, I'm going to draw some little r's now, right? I'll draw a little r right here. I'll draw a little r right here. Okay, and now notice because of the symmetry I've created here, this is also going to be a right angle. Okay, if I go from the center of this circle to the very highest point right here, I'm cutting this semicircle in half. That has to be 90-degree angle. And I've got another 45, 45, 90 right here. Okay, isosceles right triangle. So in this case, x root 2, that's the ratio of those sides. But in this case, for this 45, 45, 90, x is equal to little r. So this ratio would be r to r to r root 2. Okay, now again, I've successfully related little r to big R because I also know that that hypotenuse is equal to big R. Okay, so I'll write that out. R times root 2, little r times root 2 equals big R. Okay, I want little r over big R, so I will divide both sides by big R. I'll divide both sides by root 2. Okay, I get little r over big R equals 1 over root 2. Square that whole thing. I get 1 squared is 1, root 2 squared is 2. And there's a separate path that leads me to the same answer, D. Okay, so any thoughts on this question? What are the take-homes from this? Well, notice you'll run into questions sometimes where you aren't given any particular values, and then what you need to do is start relating the different pieces, seeing if you can come up with some algebraic expression. In this case, we wanted the ratio of areas. So my first step was, instead of trying to, work my way to this answer directly, I kind of worked backwards from what I wanted, right? I want the area of the small circle over the big circle. That's pi little r squared over pi big R squared. Thinking about it that way simplifies what I'm looking for. I'm just looking for little r over big R. Okay. Then at that point, it's kind of a question of playing around with your diagram. Drawing big R's, drawing little r's, see if there's some way you can relate them. There's a lot of big R's that you can draw that won't be useful at all. So what you're kind of hunting for is, what's that specific way of drawing a shape with big R and little r that makes them easy to relate? Now, either way you do it, in this question, you're going to run into a 45, 45, 90 that helps you get there. And the first path, again, reviews this very key idea. If you have an angle that intercepts the diameter of a circle, you're creating a right angle. Okay, we use that to our advantage to find a 45, 45, 90. Similar path over here leads you to that same 45, 45, 90. Okay, working through all that, again, leads us to the correct answer of D. All right, so that concludes the second of our geometry videos, GRE Geometry Part 2. So I hope you found those questions useful. And then in terms of take-homes, well, one thing I'd note is there's that core toolkit of geometry knowledge that you want to be really comfortable with. Not a huge amount of things to memorize, but those are going to be really useful to you on test day. In addition to that, of course, you want to be really careful when you're applying those formulas, make sure you don't make careless errors. And lastly, can you stay flexible? When you approach a question, can you thumb through your different geometry tools? So I want to think about triangles or polygons, or maybe I want to reach into my algebra toolkit. So that's what I mean by staying flexible. Can you think about all the different tools before you dive into one particular solution path? All right, well, thanks again for watching. Happy studying, and I'll see you next time.